A single bead can slide with negligible friction on a wire that is bent into a circular loop of radius 15 centimeter, as seen in the figure below. So here's the figure. Here is the wire, which is bent to a circle, and here is the bead, which is tied to it. Now, the circle is always in a vertical plane. This circle, which is in orange, is always in a vertical plane and rotates steadily about its vertical diameter. So it rotates as shown here in the figure. This is the vertical diameter, and this circle is all the time rotating in the vertical plane. When they say steadily, it means that it's with a constant velocity and with a period of 0.45 seconds, 45 seconds. Now, the position of the bead is described by the angle theta, that the radial line, which is drawn from the center of the loop to the bead, makes with the vertical. So the position of the bead on this circle, on this circular loop or circular wire, is described by this angle theta, which is nothing else than the angle between the center of the loop and this bead, where it is. Now the question is, at what angle from the bottom of the circle, so from this position here, where is the bottom, what angle from the bottom of the circle, okay, can the bead stay motionless relative to the turning circle? So if this circle is rotating steadily, okay, what is the value of theta, of the angle theta, such that the bead is motionless with respect to this, moving circle or turning circle, okay? Now, let's see how we can treat this problem. First of all, we have to see, or we have to check how this bead is moving. So if this circle is rotating in the vertical plane as shown by this arrow here, that means that the bead is describing a circle, horizontal circle, right? Like this. It's actually moving along this circular path. And this circular path has the radius r. I'll just call it, so I'll just call the radius of, so this is the radius of the wire, of the circular wire r, and let's call the radius of this, the circle along which the bead is traveling, I just call it small r, okay? Just a differentiate between both. Now, how r and r, they are related, just have a look at this triangle. So if you can see here, this is r as well. So this line, it's just a fake line. It's the line that connects the center of the wire to the bead, but it's not a wire or anything, right? It's just a fake line to say that the angle between the vertical and this line is the angle theta. Now, if you look at this triangle over here, you would just deduce that if you take sine theta, you will end up with sine theta is equal to the opposite divided by hypotenuse. So r over r. And from here we can deduce that the radius of the circle along which the bead is moving when this wire is turning is nothing else than r multiplied by sine theta. Okay, so that's it. Now, we want to know how much is the value of this angle so that the bead remains at rest. It remains motionless. To determine it, we have to apply Newton's second law, because in the Newton's second law, we can access to the acceleration, and it's only there where we can put a condition that the bead should stay motionless. That's why we should apply Newton's second law on this bead. But before to do so, what we have to do is to fix or to determine what are the forces acting on this bead, and then apply Newton's second law, and then make the projection of the forces. So I'll just draw another figure here to draw the free body diagram. Okay, so here is the circular wire. Here is the vertical diameter, and here is the bead. Okay, it is somewhere along this this wire. Now, what are the forces acting on this bead? They are the following. So first of all, you should have the weight, which is given by the mass of the bead times g, where g is the gravitational acceleration. And then since the bead, it passes through this, this circular wire, then there is a normal force, right? And this normal force is perpendicular to the point of contact between the bead and the circular wire. And so this is why the normal force is into this direction. So it's perpendicular to the tangent at this point in here. So this is the normal N. And we know that the wire is moving along this circular path, right? Now, we know that definitely it should have a radial acceleration or centripetal acceleration. And we know that the centripetal acceleration, it all the time points towards the center of the circle along which it is moving. So here is AR, right? Now, I didn't say that the bead is moving up or down. So this motion of the bead upward or downward along the circular wire is not allowed, because what we are looking for is a situation where the bead is motionless relative to the turning wire, which means that this bead is not moving up or down. It's just moving on this horizontal circle. So it is moving on a horizontal circle with a constant speed, because the wire is rotating steadily, but it's not moving upward or downward with respect to this turning wire, because this is the condition in here, okay? So now let's apply Newton's second law on the wire and then make the projection of the equation, Newton's second law equation, onto the radial axis and onto, well, whatever we will see, what are the useful axes. So we have the normal N plus mg is equal to ma. Those are the only forces acting on the bead, right? Now, let's choose two axes which look useful for us. The first axis is obviously the radial acceleration. So, or let's say let's take the centripetal acceleration. If I take the centripetal acceleration, so let's call this x-axis, okay? This is the axis that everything happens on, because we have the radial acceleration along this axis. And then we have to take another axis which is perpendicular to x and which holds on the other vectors. So since mg is pointing vertically, then let's take the y-axis to be the other axis of projection. Then we'll end up with x and y. So x is the same as the centripetal direction. It's the direction towards the center of the circle, and y is the vertical direction, which is perpendicular to x. And now all we have to do is to make the projection of these of this equation onto x and y. So projection onto x, or let's start projection onto y. We end up with now we have, this is the normal N, right? And this is mg. For mg, it's very easy. Mg is pointing in the opposite direction with respect to y-axis, and so we end up with minus mg. Along the y-axis, there is no motion. The bead is not moving up or down, so this is why it has a 0 for the acceleration term. The only thing is that we need to make the projection of this normal onto the y-axis. Okay, the angle between, so this is the normal force is perpendicular to the wire. So actually this is nothing else than the theta, which actually shows the position of the bead along this circular wire. And so we can deduce that this is nothing else than the angle theta, and the projection of N onto the y-axis is nothing else than N cosine theta. So we end up with N cosine theta minus mg equals 0. And then along the x-axis, we end up with the projection of N onto the x-axis would be N sine theta. So we end up with N sine theta. Mg doesn't have any projection onto the x-axis, it's just perpendicular to it. So N sine theta is equal to the mass of the bead multiplied by the radial acceleration AR. We don't know what is AR, but actually we know that the bead is moving steadily, which means that if you can replace AR by its expression, so we know that AR is equal to V squared divided by R, where R is the radius along which the bead is moving. So be careful here. This is nothing else than the radius R, small r, right? Okay, we don't have the value or the expression of V, the speed of the bead, But actually, we know that it's rotating steadily, just like the wire, because the wire is rotating steadily about its vertical diameter. That means that the speed is rotating steadily as well along this circular path in the horizontal plane. And so we can replace v with the expression of the period. So we have seen that the period is given by 2 pi r over v. And so from here, we can deduce that v is nothing else than 2 pi r over t. So t is known, it's given in the text in here. So all I have to do is now to replace v with 2 pi r over t. And so we end up with n sine theta equals, so we end up with n sine theta, or let's just replace everything by its value. Now, n is unknown as well in this expression, so, but we can take it from the projection onto the y-axis. We can deduce that n is nothing else than mg divided by cosine theta. So we end up with mg divided by cosine theta multiplied by sine theta. It's equal to m over r times 2 pi r squared 2 pi r divided by t, all of it squared. So we end up with 4 pi squared r squared divided by t squared. And we just have to deduce these terms. So we end up with mg sine theta divided by cosine theta equals to m, or just equals to 4 pi squared m over t squared multiplied by r. But don't forget that r is nothing else than r, capital R multiplied by sine theta, where r is known. It's actually equal to 15 centimeters, the radius of the circular loop. So we just substitute r with capital R sine theta. And so we end up with the following equation for the angle theta. So we can cancel out m on both sides, right? And so we end up with g times sine theta over cosine theta is equal to 4 pi squared r over t squared multiplied by sine theta. Now we have an equation that only depends on theta. So theta is the only unknown in this equation, and we need just to solve it. It becomes very easy. How to do so? So look, here we have two cases that we have to take care of. When you have an equation where you have the same parameter, in this case, it's a function of theta on both sides, if the value of this function is different than 0, then it becomes a number, and you can actually just cancel out a number on both sides of an equation. So this is why we have to take two cases. The first case is if sine theta is equal to 0. So if sine theta is different than 0, let's say, if sine theta is different than 0, then in this case, we can cancel out sine theta on both sides of the equation, and we end up with g divided by cosine theta equals 4 pi squared r over t squared. That's it. Because sine theta is just a number, like it's 0.5. So you can just cancel out 0.5 on both sides. And so we end up with cosine theta equals g times t squared divided by 4 pi squared times r. And so we just make you just substitute or just make a numerical application, and you end up with the value of theta. Now the other option, or the other case, would be sine theta equals 0. If sine theta is equal to 0, then you end up with 0 equals 0. And this is correct. I mean, if you have an equation where you have if this function equals 0 on both sides, you end up with 0 equals 0. And this is correct as an equation. That means that sine theta equals 0 is a solution. And from this, we can deduce that theta equals 0 is a solution as well. So what does it mean? This means that if the bead is on the bottom of the circular wire, and the circular wire just evolves or it rotates with this period, then the bead remains motionless relative to the turning circle. And the other solution is the angle theta, which corresponds to this value in here. So for this case where t is equal to 0.45 seconds, you have two possible solutions, which are these two solutions, okay? Now let's see how much is just the value of theta. So the value of theta is 70.4 degrees. So in the case where t is equal to 0.45 seconds, you have two possible cases. If the bead stays at the bottom of the circular wire, it will remain motionless with respect to the turning wire. And the other option is that the bead could be at 70.4 degrees with respect to the lower position in here, and it will remain motionless as well with respect to the turning wire. So this is for the part A. Now for the part B, you have to repeat the problem, but by taking the value of the period to be 0.85 seconds. Okay, so whenever you have to repeat the same problem, then you just have everything in hands because you already have solved it in part A. All what we need to do now is to replace, just to take the same analysis. We'll just take the result of this analysis, which is this equation, and we will just do the same reasoning. So in this case, if t is equal to 0.85 seconds, we will have either theta equals 0 as a solution, just like before. And if sine theta is equal to 0, you will end up with this value. Okay, now what you have to do is to replace t here by 0.85 instead of 0.45. But now what we end up with is that if you replace t by 0.85 in this expression, which we have up there, you'll end up with cosine theta equal 1.2. And this is impossible. This is not a solution. So from here, we can deduce that in this case, when the circular wire is rotating slowly with respect to the part A, the only solution, so the only case for which the bead would be motionless relative to the turning circle is theta equals 0. So that's it for this exercise.